Welcome to our channel Circuits Analytica. In this video, we will discuss first-order active filters. Filters are frequency-selective networks that passes signals of certain frequencies and reject other frequencies. Filters are used in various communication and signal processing systems. Based on the types of components used, filters can be classified as passive filters and active filters. In passive filters, passive components like resistors, capacitors, and inductors are used. In active filters, resistors, capacitors, and active components like ICs are used. Usage of operational amplifiers in active filter improves the input and output impedance of the filter. This is the block diagram of a first-order active low-pass filter. The first block is a passive low-pass filter which consists of resistance and capacitance, and output of the passive low-pass filter is fed to a non-inverting amplifier. This is the circuit diagram of an active low-pass filter. The first block is a passive low-pass filter which consists of resistance and capacitance, and the output of this passive filter is fed to a non-inverting amplifier with resistors RF connected between output and inverting input. Resistor R1 is connected between the inverting input and ground of the operational amplifier. For frequencies less than or equal to the cutoff frequency, capacitor acts as an open circuit and signals are applied to the input of the non-inverting amplifier. For frequencies greater than the cutoff frequency, capacitor acts as a short circuit and those signals are bypassed to the ground. So this is the condition of this active low-pass filter for frequencies less than cutoff frequency. For frequencies less than cutoff frequency, capacitor CL acts as an open circuit as capacitive reactance is very high. So, whatever be the input voltage, that voltage appears at the non-inverting input of the operational amplifier, and output of the non-inverting amplifier is equal to V0 is equal to voltage at the non-inverting input V1 into 1 plus RF by R1. So for frequencies less than the cutoff frequency of the filter, as V1 is equal to V in, we can write output voltage V0 is equal to V in into 1 plus RF by R1. For frequencies greater than the cutoff frequency, capacitive reactance is very small. Capacitor acts as a short circuit. So, voltage at the non-inverting input is equal to 0 as non-inverting input is pulled down. So, V1 is equal to 0. As V1 is equal to 0, output voltage V0 is equal to voltage at the non-inverting input into 1 plus RF by R1. That means output voltage V0 is equal to 0. Now this is the derivation for cutoff frequency FL and the transfer function of the active low-pass filter. So V1 of S is equal to V in of S into 1 by SC, the whole divided by R plus 1 by SC. We can rewrite V1 of S as V1 of S is equal to V in of S divided by 1 plus SRC. So output voltage V0 of S is given as V naught of S is equal to 1 plus Rf by R1 into V1 of S. That means V naught of S is equal to 1 plus Rf by R1 into V in of S divided by 1 plus SRC. So we can write transfer function H of S is V naught divided by V in, that is equal to 1 plus Rf by R1 into 1 by 1 plus SRC. Put S is equal to j omega in the equation for H of S. 1 plus Rf by R1 is equal to A naught and 1 by Rc is equal to omega H. So we will get upper cutoff frequency of the low pass filter is f of h is equal to 1 by 2 pi Rc. So this is the frequency response of a low pass filter. 1 plus Rf by R1 is the gain of the non-inverting amplifier, and that is the maximum gain of this active low pass filter. So for all frequencies less than cutoff frequency f of h, gain of the circuit is greater than or equal to 0.7 into 1 plus. When frequency of the input signal is equal to f of h, gain of the active low pass filter is equal to 0.7 into 1 plus Rf by R1. And from this value onwards, if we increase the frequency beyond this value f of h, we can see that the gain falls. Thanks for watching Circuits Analytica. Enjoy learning. Please comment, like, share and subscribe our channel.